Hello everyone, welcome to the channel Learn Math with the Shobita. Today I am back with some collection of questions from linear algebra. First question, let V of R be a vector space over the real field R of all real valued functions defined on R. Then which of the following sets is not a vector subspace of V of R? So here in the given options we have to choose a set which is not a subspace. Okay, so what do you mean by a subspace? What do you mean by a subspace? Let us see. A subset W of V is a subspace if it has these three properties. If any two vectors are in W, say W and W dash are in W, then their sum, that is W plus W dash, is also in W. For any scalar C, if W belongs to W, then C into W belongs to W. The zero vector is in W. That is, a set is said to be subspace of a vector space V if that set is closed under addition and scalar multiplication, and also zero vector belongs to that set. Okay, so let us check the options A, B, C, D one by one. I will call the set as A given in the option A. So let A is given by f set of all functions such that f of 1 equal to 0. Now let us verify whether it is a subspace or not. So let us take two elements in A, f comma g belongs to A and C be any scalar. Then by the definition of the set, f of 1 equal to 0, g of 1 equal to 0. Then f plus g of 1 you will get it is 0. Similarly, c into f of 1 you will get it is 0. So it satisfies the condition. So f plus g belongs to A and cf belongs to A. Further, 0 function also belongs to A because 0 of 1 you will get 0. Okay, hence A is a subspace of V of R. Option A is a subspace. We have to choose here which is not a subspace. Okay, next second one. Second one is given like set of all functions in V of R such that f of 3 is equal to f of 1. So let us check whether it is a subspace or not. Let fg be any two functions, c be any scalar, then f of 3 equal to f of 1, g of 3 equal to g of 1. Clearly 0 belongs to B. B is the set I have given in the question. Okay, option B. Okay, so 0 vector belongs to B. Also f plus g of 3, f of 3 plus g of 3 is equal to f of 1 plus g of 1 equal to f plus g of 1. So it satisfies the condition. Therefore f plus g belongs to B. Similarly, c into f scalar multiplication also belongs to B. That is, B is closed under addition and scalar multiplication. Therefore B is a subspace. Further, let us check option C. So option C, here the set is given by set of all f belongs to V of R such that f of 0 equal to 2. It is not a subspace because the 0 function does not belongs to this set C. Also f plus g of 0 you equal to f of 0 plus g of 0, that is 2 plus 2 4, which is not equal to 2. That is f plus g of 0 is not equal to 2. F plus g of 0 is not equal to 2. Therefore f plus g does not belongs to C. Also 0 vector is not in the set C. Hence set C is not a subspace. Further, the option D. In the option D they have given the set of all continuous functions. We know that set of all continuous functions is a subspace because the sum of any two continuous function is continuous and the scalar multiplication of a continuous function is continuous. Also 0 function is continuous. Hence all these three conditions are satisfied by the set D. Hence D is a subspace. So here the correct option is option C. It is not a subspace. Next question, let A from is given by 1, 2, minus 3, 4, minus 2, minus 2, minus 3, 2, 1. Then which of the following statement is true? So let us check. First we will check determinant. So determinant of A, you know how to calculate determinant. Determinant of A equal to 0. Since determinant of A equal to 0, A is an invertible is not possible. We know that a matrix is invertible if and only if determinant of A is not equal to 0. So since here determinant of A equal to 0, A is not invertible. Also for every vector B belongs to R3, the system has unique solution. This is also not possible because here A is not invertible. Here the unique, if A is invertible, then unique solution is given by x equal to A inverse B. Okay, so it has no unique solution. Further, rank of A equal to 3. This is also false because here determinant of A equal to 0 implies rank of A is less than 3. Since determinant of a matrix is product of eigenvalue, which is equal to 0, so therefore 0 is an eigenvalue of A. This option is correct. Next question, let B is given by 2 by 2 matrix 1 minus 1 2 minus 1 is a linear transformation defined on R2, then which statement is false? We have to select the false statement. So this is related to characteristic polynomial, eigenvalue, eigenvectors, all about that. So let us first find characteristic equation of this. So characteristic polynomial of a 2 by 2 matrix is given by t square minus trace of A into t plus determinant of A. Here trace of A equal to 0 and determinant of A is equal to 1. Therefore characteristic polynomial is given by t square plus 1, which is equal to if you solve it you will get t equal to plus or minus I. So therefore this matrix B has two distinct complex eigenvalues. So t square plus 1 is a characteristic polynomial. This is true. B has no eigenvalue in R. This is also true because here the eigenvalues are complex. B has no eigenvectors in R2. This is also true because if a matrix has eigenvalues, complex eigenvalues, then it has no eigenvectors in the real. That is eigenvectors in the R2. Okay. Or in general Rn, it has no eigenvector. If the eigenvalues are real, then it has eigenvectors in R2. Okay. Further, here the option B is a diagonalizable matrix. Okay, matrix. This statement is false because here they have given complex eigenvalues. So this matrix is not diagonalizable matrix over R. But this matrix is diagonalizable over complex field. Since it has two distinct complex eigenvalues, this matrix B is diagonalizable matrix over C. Suppose they have given the option here it is over R, then this statement is the false statement. Okay, if they have given it is over C, then it is the true. It is diagonalizable over C. It is not diagonalizable over R. Next question, find the rank of the given matrix. The here given matrix is 4 by 3 matrix, not a square matrix. So how to find here rank? The rank is nothing but maximum number of linearly independent row vectors or column vectors in the matrix A. So let us reduce this matrix into a row echelon form. So I will apply the row transformation like this. So if you apply R2 changes to R2 minus 2R1, R3 changes to R3 plus 2R1, R4 changes to R4 plus R1. So see the calculation, pause the video and see the calculation. You will get like this after this elementary row transformation. Next, applying the successively elementary row transformation, the matrix reduces to this form containing one complete zero row. Therefore, here rank of A equal to 3 because it has 3 linearly independent row vectors. So it is rank of A equal to 3. So in general, what about the rank of M by N matrix? Let us see. Okay, this is some points which will be helpful for you. For a N by N matrix, there is no ambiguity in the finding the rank of a matrix because it has number of columns equal to number of rows. Here in the case of M by N matrix, what is this? Let us see. Let A be an M by N matrix over F. Then the row rank of A equal to maximum number of linearly independent row vectors. Column rank of A equal to maximum number of linearly independent column vectors of A. Okay. The row rank of an M by N matrix is at most n as dimension of Fn equal to n. Column rank of an M by N matrix is at most m as dimension of Fm equal to m. See, an M by N matrix is a mapping from Fn to It is a linear mapping from Fn to Fm. So row space is subspace of Fn and column space is subspace of Fm. So row rank of m by n matrix is at most n and column rank of m by n matrix is at most m. Okay, now for any m by n matrix A, the rank of A is defined to be the common value of row rank of A and the column rank of A. Therefore, rank of A is less than or equal to minimum of m comma n. Okay, this is the point you have to remember. Next question. Let L from R3 to R be given by L of xyz is equal to 3x minus 2y plus z. Then this is a linear transformation. So here we have to choose the correct one. Okay. According to rank nullity theorem, we know that rank of T plus nullity of T equal to dimension of domain. Okay. Here domain is equal to R3 and its dimension is 3. What do you mean by rank of T? Rank of T is nothing but dimension of image of T. Nullity of T is equal to dimension of kernel T. Okay. So here domain is equal to R3, therefore dimension of image of L plus dimension of kernel of L equal to 3. So from this we can conclude that dimension of image of L equal to dimension of kernel of L is not possible. Okay, if they are equal then it should be an even number. It is not possible, so option D is false. Further, let us calculate the kernel L. Kernel L is set of all xyz such that L of xyz equal to 0. So simplifying we will get z equal to minus 3x plus 2y. And here x and y are free variables. So put x equal to 1, y equal to 0. So one vector is 1, 0, minus 3. Put x equal to 0, y equal to 1. So you will get 0, 1, 2, another vector. So these two vectors are linearly independent and it spans kernel L. Therefore, this is the basis for kernel L. Hence dimension of kernel L equal to 2. So by rank nullity theorem, dimension of image of L is equal to 3 minus dimension of kernel of L. So 3 minus 2 you will get 1. So dimension of kernel L equal to 2. Dimension of image L is equal to 1. So here the correct option is dimension of kernel L is equal to 2. Option C is correct and other options are wrong. Next question. Let A be a 2 by 2 matrix ABCD where ABCD belongs to the set 0, 1. Then the number of such matrices which have inverse is. So we have to find the number of matrices which are invertible. So what do you mean by GLN of FP? GLN of FP is the set of all invertible n by n matrices. So its cardinality is given by, that is the number of elements in GLN FQ. FQ is the field containing Q elements. N is the order of the matrix, is given by product K equal to 0 to n minus 1 Q to the power n minus Q to the power K. Here n is equal to 2, Q is equal to 2. So applying this we get total number of elements or total number of 2 by 2 invertible matrices. Total number of 2 by 2 invertible matrices is given by apply this formula. Here k equal to 0 to n equal to 2, so 0 to 1. So for k equal to 0, 2 square minus 1. For k equal to 1, 2 square minus 2. So simplifying you will get 6. So there are 6 elements are there, or 6 matrices which have inverse. Okay. Next, another point. Here suppose they have asked to evaluate the matrices having determinant 1. Then this group is called SLN-FQ and its cardinality is given by product k equal to 0 to n minus 1 q to the power n minus q to the power k divided by q minus 1. Suppose they have to ask the number of matrices having determinant 1, then this is the formula. Next question. Let V equal to R2 be a vector space over R. Let alpha equal to 1, 2, beta equal to 2, 1, gamma equal to 2, 4 in V. Then we have to check whether alpha, beta are linearly independent or dependent, or alpha, gamma are linearly independent or dependent. The one simple trick to check whether they are given set of vectors are linearly independent or not, it is enough to check the determinant. If determinant of these two vectors is writing like this equal to we get 0, then the given pair of vectors are linearly dependent. If the determinant is not equal to 0, then the given pair of vectors are linearly independent. So let us check for alpha and beta. So we got determinant is not equal to 0, therefore alpha beta are linearly independent. Now let us check for alpha and gamma. While finding the determinant, we got it is 0, therefore alpha and gamma are linearly dependent. So option alpha beta are linearly independent and alpha gamma are linearly dependent. Thank you friends. Please share and subscribe the channel.